This week we dive into our host galaxy, the Milky Way galaxy, as well as other galaxies. So notice that this week I say chapter 23/24, chapter 22/23, and 23/24, and that's because the 10th edition and the 9th edition of the books have these chapters in different numbers. But it's just we're studying the Milky Way galaxy and other galaxies. So let's start off with a concept question. So which of the following rankings is correct for the size or width of the following objects from smallest to largest? So take a moment to think about this and then go to the next slide. Okay, now you probably answered D, with the planet being smallest all the way to the largest being the universe. You also could have answered A. If you remember back to our previous studies, there are some stars that can get as small as planets. Remember those brown dwarf stars? They were the size of Jupiter, or even a white dwarf star, which is all the way down to the size of the Earth. So this question, the solution could also be answer A, if you really think back to all the different types of stars that we've talked about. Okay, so what is a galaxy? A galaxy is an immense collection of stars and interstellar matter, much larger than a star cluster. So we see our galaxy as a band around the sky, and we have an edge-on view because we are on the inside of our galaxy. So if you ever get a chance to go out to a dark sky away from city lights, you have the chance to see the inner workings of our Milky Way galaxy. So the Milky Way galaxy is in a plane, a disk, and we are in that disk of stars and gas and dust. And so when we look in the night sky, we see the Milky Way galaxy as a band shooting across the night sky. So these are just two images. So hopefully you have a chance, if you haven't gotten one yet, to go out to a really dark area and view the Milky Way galaxy in our night sky. So let's take a look at this picture in a little bit more depth. Take a look at some of the white areas within the band of the Milky Way. What is the bright, sometimes called milky area that we see in the Milky Way galaxy? Take a moment to think about this. What do you think it is? All right, after you've taken a moment to think about it, these are all the stars. Okay, the stars are compacted so close together, they're so dense, that to us we can't even distinguish between individual stars. That's how dense it is in there. So that milky white area are stars. Okay, take another look. What's the dark area that we see as part of the Milky Way galaxy? Take a moment, pause the video, and think about it. What is the dark area? Okay, hopefully you've thought about it and could come to the conclusion that this dark area is the gas and dust that's blocking out that background starlight area, showing you that our Milky Way galaxy is made up of stars, gas, and dust. Okay, so one of the ways we like to look at our Milky Way is by looking at the different wavelengths of light. So here's two infrared images of our Milky Way, glowing in the infrared. So what does this show you? Shows you that there's a lot of gas and dust in our Milky Way galaxy. Okay, so our view. So here's a very rudimentary kind of artist rendition of our galaxy. It's a disk, okay, of stars and gas and dust. We exist somewhere out in the spiral arms, kind of towards the edge. So when we look up or below that disk of our galaxy, we see relatively few stars. But when we look into the plane of our galaxy, that's where we see the Milky Way. And that's why we see the Milky Way as a band across the night sky. Something like this. So looking into the plane of our galaxy, and then looking above and below, okay, out of the plane of our galaxy. But we might be looking out of the plane of our galaxy, but we're still looking at stars that are within our own galaxy. Because stars above and below the Milky Way galaxy only go about 1,000 light years. So really, every star that we see in the night sky is within our own galaxy. So here's the kind of basics of our galaxy. Okay, we have the disk, which is about 50,000 parsecs in diameter, and it's about 60 parsecs thick. This is about 100,000 light years across and about 1,000 light years thick. Our disk has a high concentration of interstellar gas and dust. In the galactic center, we have what we call the central bulge. The bulge is not perfectly symmetrical, and we think at this point it may have kind of a bar or peanut shape to it. Now, around the disk of our galaxy, we are surrounded by a spherical distribution of globular clusters and older stars in what we call the galactic halo. So let's take a look at what this looks like. Okay, So looking at the edge-on schematic view of our galaxy. The diameter of our galaxy is about 100,000 light years across, and here's the thickness, okay, about 1,000 light years thick, with a large central bulge. This is the disk of the galaxy, surrounded by this halo of globular clusters. Notice our sun's location is about 25 to 28,000 light years from the center, so we're somewhere kind of near the edge of the disk. Now, if we took a top-down view of the galaxy, you'd see that that disk has large spiral arms, and our sun is sitting in one of these spiral arms. So here's a central bulge in these spiral arms. Take a look at the color differences here of the Milky Way galaxy. What do you notice? Okay, so let's start with a concept question. Imagine that you could travel at the speed of light. Starting from Earth, approximately how long would it take you to travel to the center of the Milky Way galaxy? Pause the video and then answer, and flip to the next slide. All right, hopefully you answered around 25,000 years, okay? Because if you could travel the speed of light, and it's about 25 to 28,000 light years to the center, that's how long it would take you to get there. Let's try another one. When we observe stars near the center of the Milky Way galaxy, we detect light that is emitted from those stars about how long ago? Pause the video and take a moment to answer the question. All right, once again, they're about 25,000 years old because that's how far away they are in terms of how we see looking back in time. All right, another one. An observer far outside our galaxy would best describe our galaxy and the sun's position in it as which of the following? All right, letter A. A disk of stars with our solar system near the edge. So hopefully you could rule out some of these other answers, okay? The disk of stars centered on our solar system? No, definitely not. A disk of stars with a bulge containing our solar system? No, we're not in the bulge. And a sphere of stars? Nope, it's not a sphere, it's a disk. All right, so there's about 200 billion stars in the Milky Way's galaxy, central bulge, and the halo. Okay, there's a lot of stars in our galaxy. And our sun lies within that galactic disk about 25 to 28,000 light years from the center. Now we orbit around the center of our galaxy, and we're whizzing through the galaxy at a speed of about 800,000 kilometers per hour. This means that it takes our solar system, our sun, about 200 million years to complete one orbit around the center of our Milky Way galaxy. It takes a while, although we are booking it. Okay, so I didn't talk about this last time in terms of stellar evolution, but stellar evolution has produced two curious stellar populations within our galaxy. So two types of stars, population 1 stars and population 2 stars. Population 1 stars are members of what we call a second generation of stars. Stars like our sun. They're relatively young and they're metal rich. So metal rich, astronomers use the word metal very loosely. Okay, a metal in astronomy is any element heavier than hydrogen. So the spectra of these stars contain prominent lines of these heavy metal rich elements. So these are stars that are forming in a time that the universe has already been populated with heavy elements from the death of earlier stars. So these are called population 1 stars. They're our newer generation. Population 2 stars are the older generation of stars. They're part of a first generation of stars that were born out of a universe that was primarily devoid of these heavy elements. Okay, so these heavy elements are only about 3% as abundant in these stars as they are in the sun. So these two different types of stars, these older, redder, kind of deader stars, and the younger, bluer stars that are just being born. So those globular clusters that exist out in the halo, these are tight, gravitationally attracted groups of stars. They're in a spherical shape, and they contain these old, red, population 2 stars. And what's kind of cool about globular clusters is we can use them based on the star's age to help us determine the size of our galaxy. Okay, so let's look at how the stars, what kind of stars exist in the different parts of our galaxy. So we have the halo, okay, those old, red, and dead population 2 globular clusters. Then within the disk, we have young, metal-rich population 1 stars like our sun. Okay, there's a lot of star formation happening in the disk. Okay, stars appear blue in color. Okay, and we see a lot of those O and B main sequence stars. There's a lot of active star formation happening within the disk. That central bulge contains a mixture of both population 1 and 2 stars, so both old and new. That's why it looks kind of yellowish or kind of reddish in color compared to those blue spiral arms. We don't really see any short-lived blue O and B type stars, and not really necessarily a ton of star formation going on. Okay, so let's take a look at a galaxy similar to ours and what this looks like. So here's our central bulge made up of that mix of population 1 and population 2 stars, and then the spiral galaxies within the disk, primarily made up of those young population 1 stars. Notice the blue color versus the yellow-red color in the center. Okay, if we take a look at our Milky Way galaxy in the different wavelengths of light, similar to how we've done here with the galaxy M83, we can of course see a more clear picture. So on the left we have the visible images, and then we go to the radio, and then finally the infrared. Take a look at where these wavelengths of light are populated within the galaxy. Notice that the infrared is glowing in those spiral arms. So those spiral arms are containing a lot of that gas and dust. Okay, our galaxy is rotating. This is an image of M51. And what we see from this galaxy is that the spiral arms are rotating around that central bulge. Our Milky Way galaxy is moving in a similar fashion to M51. Okay, so let's do another conceptual question. Compared to stars like the Sun and the disk of the Milky Way, stars that populated the extended spherical halo of the galaxy were born when? So I'm wanting you to compare the age of the stars in the disk compared to the stars in the halo. So take a minute, pause the video to answer the question. All right, hopefully you answered C. Okay, these stars were born earlier from more nearly primordial material, so have fewer heavy elements. So primordial means like the beginning, so towards the early beginnings of the universe. Okay, so another cool feature about our galaxy is at the very center of our galaxy is a black hole. Okay, so data from infrared and radio observations, we can look through all that interstellar absorption. What do we see? We see that Sagittarius A star, that's how you say it, Sagittarius A star, is a radio source at the center of our galaxy. Okay, stars are orbiting around Sagittarius A star, so it is exerting a large force on these stars. So therefore it must be massive. And what it is it's a supermassive black hole with a radius of about 45 astronomical units. So that means the radius of this black hole is about the size of our entire solar system. So here's zooming in to this area of Sagittarius A star, looking towards the center of our galaxy. We zoom in, looking at the radio waves and the X-ray waves. We see a lot of energy coming from this region where this black hole is. Okay, so take a look at this video here. I'll pause the video and I'll get it showing here. This is how we've discovered that we have a black hole at the center of our galaxy. These are all stars, S0, 16, 4, 1, and so forth. Those are stars, and it's taking data over multiple years, from 1995 to 2003, and then the video is going to show you all the way to 2011. And we're looking at positions of the stars in the night sky, and then projecting out the full orbital period of that star. And what we see is that these stars are being gravitationally tugged by a large force, this black hole at the center of our galaxy. So I'm going to get the video up to show you. Okay, so the center is the black hole. Notice the time, okay, the years ticking by. And this is the motion of those stars around that central black hole. So let's take a look at it one more time. Okay, so there's the black hole in the center. Here's the position of the stars starting in 1995. Then they're taking data and projecting out that orbital period of these stars from 2006 and then up again until 2011. So we're really able to see the full motion of these stars, indicating that there's a supermassive black hole sitting at the center of our galaxy. Okay, I'll stop here and I'll continue the lecture in the next video.